Good afternoon, student. Myself Satanam Singh, lecturer electrical engineering, Government Polytechnic College, Mohali Khundi Majra. Today we will discuss the topic basics of electrical machines 1. In this lecture, we will discuss that topic of overview of electrical machines, construction of electrical machines, principle of operations, types of DC generator and types of DC motors. Learning objective of this lecture is to state the principle by which machines convert mechanical energy into electrical energy, discuss the operating difference between different types of generator and motors, understand the principle of DC generator and DC motors. So, first is overview of electrical machines. So, student, what is the machine? Machine is a electromechanical energy conversion device. Machine is a electromechanical energy conversion device which convert the form of energy, that is from mechanical energy into electrical energy or from electrical to mechanical energy. So, machine is a electromechanical energy conversion device which convert either electrical power or electrical energy into mechanical energy or mechanical power, or it convert mechanical energy or mechanical power into electrical energy or electrical power. So, if this electromechanical energy conversion device convert electrical energy or electrical power into mechanical energy, then it is called motor. If it convert mechanical energy into electrical energy, then it is called generator. Depending upon the working of the machines, the electromechanical energy conversion device may be named as generator or motors. Overview of electrical machines. This is a simple overview of electrical machines. It consists of two parts, mainly two parts, stator and rotors. This is the stator part, which is stationary, and this is the rotor part, which rotates. So, this rotor is mounted on a shaft, and this is the end housing containing bearing. So, this is the end housing which contains the bearing here. So, first one is generator. Generator is a machine that convert mechanical energy into electrical energy by using the principle of magnetic inductions. So, basically it consists of two main parts, that is stator and rotor. Stator is a magnet and rotating part is a elementary coil. So, magnetic lines of force, that is magnetic flux, will flow from north to south magnet, and this elementary coil, when this elementary coil cut the magnetic flux, and EMF will induce in this elementary coil. Brushes, this is the sliding contact, that is brushes. These brushes are uses to collect the current from the this rotating elementary coil. Generator actions. So, this is the diagram of elementary coil rotating in a stationary magnetic field between a pair of magnetic poles. So, in a generating action, two magnets, that is north and south, magnetic flux will flow from north to south. When we apply mechanical torque to this elementary coil will rotate in the same direction that applied mechanical torque. So, this rotor, that is rotating coil, will rotate when we apply the mechanical torque from the prime mover. When this elementary coil rotate, it will cut the magnetic flux. When it cut the magnetic flux, an EMF will induce in this elementary coil, or you can say conductor. This is according to Faraday law, which states that whenever flux linking with the conductor changes, an EMF induced in the conductor. So, this is the first action, that is we apply the mechanical torque, and this coil rotate and cut the magnetic flux. When it cut the magnetic flux, and EMF will induced in the rotating coil, and current start flowing through the load resistance R. So after this, second action will start, that is current carrying conductor placed in a magnetic field. When current carrying conductor placed in a magnetic field, and force will experience on the conductor. So another torque, that is TE, will produce, which act in the opposite direction to the input mechanical torque. So according to second action, when current carrying conductor placed in a magnetic field, and force will exert on the rotor, which will act in the opposite direction to the input mechanical torque. So next part is that TF, that is frictional torque, which it has to overcome. So figure shows the elementary coil rotating in a stationary magnetic field between a pair of magnetic poles. Let it rotated in an anti-clockwise direction at an angular velocity of omega radian per second by some prime mover, giving the generator a mechanical torque Tm. The coil sides or conductor cut the magnetic lines of force, and hence an EMF is induced in the coil. So when conductor cut the magnetic lines of force, an EMF will induced in the coil, which is the statement of Faraday's law. The coil is further connected to an external resistance R, therefore current I flow through the coil side as well as through the load resistance R. The direction of current is marked on the coil sides. Now the second action start, that is current carrying coil or conductor is placed in a magnetic field, and hence the conductor will experience a force or torque Te. The direction of torque will be opposing to the driving torque Tm. So this is the input torque, that is Tm. So Tm will be equals to Te plus Tef. So mechanical torque has to overcome electrical torque and frictional torques. If we multiply torque with the omega, that is angular speed, then it will come out to be a power. So as you know, power is equal to omega into T. So when we multiply this equation with omega, then omega Tm is equal to omega Te plus omega Tf, where omega Tm is the mechanical input power, which is applied from the prime mover. Omega T is the mechanical power available for the conversion into electrical power. So omega T is the mechanical power which is available for the conversion into electrical power. Omega T is the mechanical power lost due to friction. So the power which is lost due to friction is omega Tf. Next is Faraday laws of electromagnetic inductions. There are two definitions of Faraday law of electromagnetic inductions. First one is, whenever a conductor cut across a magnetic field, an EMF is induced in the conductor. As we seen in this diagram, whenever conductor cut across the magnetic lines of force, an EMF induced in this conductor. And second is, when the magnetic flux linking with any circuit or coil changes, an EMF is induced in the circuit. So here you can see, when magnetic flux linking with this coil changes, an EMF induced in this conductor, which is shown on this galvanometer. If you observe this diagram, when magnet moving near and away from this coil, the deflection of voltmeter is in one direction when it is moving near to the coil, and in another direction when it is moving away from the coil. So the deflection in the galvanometer needle shows that EMF is induced in the coil. The direction of induced EMF in the coil depends upon the direction of magnetic field and the direction of motion of coil. EMF induced in the coil only when flux linking with the circuit changes, that is either a magnet or coil is in motions. Motor. And motor is a machine that converts electrical energy into mechanical energy by supplying a electrical power, voltage or current. Motor actions. So Previously we will discuss the generator action. Now we are going to discuss the motor action. Same machine which is used as a generator now used as a motor. So the difference is the input. In generator the input is mechanical torque, but in the motor actions input is electrical torque. So when we apply the so first we replace the load with the battery. When we connect the battery here, the current will start flowing in the conductor. So first action will start, that is current carrying conductor placed in a magnetic field. So according to this, whenever current carrying conductor placed in a magnetic field, a force will experience, that is which will rotate the rotor in the direction of applied current. So T is the electrical torque which is generated with the help of electric current. So input is TE. Accordingly our rotor will rotate in the same direction to the electrical torque. So first action is this. Now second action is when this rotating coil rotate in a magnetic field, it will cut the magnetic lines of force. Again an EMF will induced in this circuit, and current start flowing. The EMF induced due to this flux cutting, the direction of this induced EMF will be the opposite to the applied input voltage. So now the current I will start flowing through the coil. The current carrying conductor produce a magnetic field Fr. The field Fr tries to come in line with the main field Fm. Thus an electromagnetic torque Te is developed in the coil is anti-clockwise direction. Therefore coil start rotating in an anti-clockwise direction, say at an angular speed omega radian per second. Now again the second action start. When the coil moves in the magnetic field, flux is cut by the conductor and hence an EMF is induced in them. The direction of this induced EMF will be opposing the course due to which the EMF is induced. Thus the induced EMF will be opposing the supply voltage V, and the current in the coil will flow due to the difference between V and E. If R is the resistance of the coil, then applied voltage V equals to E, that is EMF induced due to the flux cutting, plus IR. If we multiply both sides by I, we will get Vi is equal to EI plus I square R. Here Vi is the electrical power input to the machine, EI is the electrical power available for conversion into mechanical power, and I square R is power loss due to resistance of the coil. Next is construction of machines. Main part of DC machines are, first one is field magnet frame or yoke, pole core and pole shoes, pole coil or field coil, armature core, armature winding, commutator, brushes, brush holder, bearing, shaft. So first part is field magnet frame or yoke. So this outer covering is called field frame or yoke. The main the purpose of using yoke is it serves the following purpose. First one is it provides the mechanical support for the poles. It provides mechanical support to these poles. It acts as a protective cover against the mechanical damage. It provides the passage for the magnetic flux produced by the poles. So this outer covering is called yoke. Pole core and pole shoes. The pole core itself may be made of solid piece of cast iron or cast steel, but pole shoes is laminated and is screwed to the pole face by means of countersunk screw. The pole core may be made of thin lamination of steel lifted together. This types of pole is held in position with the frame by means of bolts. The pole shoes serves two purposes as under. First one is it supports the pole coils. Second one is being a larger cross sections, it spread the flux and also reduce the reluctance of magnetic path. So student, this part is pole core and this wider part is pole shoes. So the purpose of pole shoes is to, first one is to carry the these field winding, these are the windings, and second is due to larger cross section area than the pole core, it spread the flux and also reduce the reluctance of magnetic path. This is the pole core and this is the pole shoes, and these are held with the yoke, outer covering of machine. Next is armature. The armature core is cylindrical in shape. It is rotating part of the machine. Its body is made up of soft iron stamping or lamination to reduce the eddy current losses. The laminations are keyed to the shaft. These are insulated from each other by varnishes. At the outer peripheries, slots are cut. The armature conductor are placed in these slots. The armature core serves the following purposes. First one is it provides the path of low reluctance to magnetic flux. Second is it houses armature conductor. So this is the armature and it provides the low reluctance path to the magnetic flux, and slots are made on this armature and conductor are placed in these slots. Next is armature winding. The armature coils are usually former wound. The conductor are placed in the armature slots which are lined with the tough insulating material. The slot insulation is folded over the armature conductor placed in the slots and is screwed firmly by bamboos or fiber wedges. The armature windings are usually of conductor covered with a single cotton cover, double cotton cover or enameled wire. On the basis of connection, these are of two types. First one is lap winding, second one is wave winding. Lap wound armature. In lap wound armature, the windings are connected in parallel. These are used for low voltage and high current applications. Armature are constructed with large wire because of high current and are used in the starter motor of almost all automobiles. The winding of lap wound armature are connected in parallel. This permits the current capacity of each winding to be added and provides a higher operating current. Number of current path is equals to 2 times number of pole. C is equal to 2P, and where C is the number of current path and P is the number of poles. Next is wave winding. Wave wound armature are used in a machine designed for high voltage and low current. Their winding connected in series. When the windings are connected in series, the voltage of each winding add, but the current capacity remain the same. And these are used in small generator, and number of current path is equals to 2. So in lap winding, number of current path is 2 times number of poles, and these are used for low voltage and high current applications. And in the wave wound, number of current path is 2, and these are used for high voltage low current applications. In wave wound, windings are connected in parallel. In lap wound, windings are connected in series. So here you can see clearly in lap winding, the windings are connected in parallel, and in wave windings, windings are connected in series. Next is field winding. Most DC machines use wound electromagnet to provide the magnetic field. When current passes through these coils, they electromagnetize the poles, which produce the necessary flux, which is cut by the armature conductor when in motion. Two types of field windings are used. One is series field winding and second one is shunt field winding. As we discussed earlier, uh, we use the permanent magnet in this diagram, but in actual we use the electromagnet instead of using the permanent magnet, and this electromagnet is produced with the help of field winding. So field winding are used to produce the electromagnet. Series field winding. Series field windings are so named because they are connected in series with the armature and are made with relatively few winding turns of very large wires and have a very low resistance. Usually found in large horsepower machines wound with the square or rectangular wires. The use of square wire permits the windings to be laid closer together, which increase the number of turns that can be wound in a particular space. Square and rectangular wires can also be made physically smaller than round wire and still contain the same surface area. So field winding are named series field winding because in series field windings are connected in series. As field winding are connected in series with armature, so the resistance of series field winding should be low, so that voltage drop across series field winding should be minimum. Shunt field winding. Shunt field winding is constructed with relatively many turns of small wire, thus it has a much higher resistance than a series field winding. It is intended to be connected in parallel with or shunt with the armature. High resistance is used to limit current flow through the field. Next part is commutator. Commutator are used to convert AC into DC. The commutator is cylindrical in structure and is built up of wedge-shaped hard drawn copper segment. The segments are insulated from each other by a thin sheet of high quality mica to prevent them from flying out under the action of centrifugal force. The segments are provided with V-grooves, which are insulated by conical mica night rings. The function of the commutator is to facilitate the collection of current from the armature and to rectify the AC induced in the armature into DC. Brush holder and brushes. Brushes are sliding contact. The function of brushes is to collect the current from the commutator and supply it to the external load circuit. These are usually made up of carbon and are rectangular in shapes. These brushes are housed in a brush holders. These are held in a position under spring tension. The pressure of the spring can be adjusted by altering the position of lever in the notches. Copper brushes are only used for machine delivering large current at low voltage. So brushes are sliding contact and are used to collect the current from the rotor, and in the case of motor, it deliver the current to the rotating part with the help of brushes. So brushes is used to deliver in the case of motor and collect in the case of generator. And brushes are usually made of carbon. In large machine delivering large current at low voltage, copper brushes are used. Bearing. These are supported in end cover. Because of reliability, ball bearings are usually employed. So for heavy duty, roller bearings are employed. These are used to reduce the friction and have less wear and tear. Bearings are used to reduce the friction and it has less wear and tear. Shaft. The material of the shaft is mild steel. It is used to transfer mechanical power from or to the machines. The rotating part For example, armature, commutator are mounted to the shaft. Next is principle operation of generator. Whenever a conductor is moved within a magnetic field in such a way that the conductor cuts across the magnetic lines of flux, voltage is generated in the conductor. The amount of voltage generated depends on, first one is strength of magnetic field, angle at which conductor cuts the magnetic field, speed at which conductor is moved, and the length of conductor within the magnetic field. The polarity of voltage depends on the direction of magnetic lines of flux and direction of movement of conductors. The polarity of voltage or current induced depends upon the direction of motion of conductor and direction of magnetic flux. To determine the direction of current in a given situation, the left hand rule for a generator is used. According to this rule, when we stretch the left hand, if thumb represents the direction of conductor is being moved, and forefinger represent the direction of magnetic flux, then the middle finger will represent the point in the direction of this middle finger will point in the direction of current flow in an external circuit to which a voltage is applied. So this is the elementary generator. To discuss the DC, before discussing the DC generator, first we will discuss the AC generator, then we will shift to the DC generator. The simplest elementary generator that can be built is an AC generator. Basic generating principles are most easily explained through the use of elementary AC generator. For this reason, the AC generator will be discussed first, the DC generator will be discussed later. And an elementary generator consists of wire loop mounted on the shaft so that it can be rotated in a stationary magnetic field. This will produce an induced EMF in the loop. Sliding contact connect the loop to an external circuit load in order to pick up or use the induced EMF. So it consists of two magnets, north and south. Flux will flow from north toward the south. In between the magnetic flux, magnetic lines of force, an elementary coil is placed, and whenever this elementary coil cut this magnetic lines of force, an EMF induced and current will flow through this resistor, and current will be collected through these two slip ring and brushes. These brushes are sliding contact on the these two slip ring. The pole piece north and south provides the magnetic field. The pole pieces are shaped and positioned as shown to concentrate the magnetic field as close as possible to the wire loop. The loop of wire that rotates through the field is called the armature. The end of the armature loops are connected to ring called slip ring. They rotate with the armature. The brushes, usually made of carbon with wire attached to them, ride against the rings. The generated voltage appear across these brushes. As an end view of the shaft and wire loops is shown at this particular instant. The loop of wire, black and white conductor of the loop, is parallel to the magnetic lines of flux and no cutting action is taking place. So since the lines of flux are not being cut by the loop, no EMF is induced in the conductor and the meter at this position indicates 0. So two coil side are represented by these two loops of white color and black color. So as we discussed, the EMF induced in the conductor depends upon the first one is magnetic lines, strength of magnetic lines of force. Second is angle subtended by the coil. to cut the magnetic lines of force. So at 0 degree angle, the elementary coil will elementary coil is in parallel with the magnetic lines of force. So the flux cutting at this position will be 0. So if flux cutting is 0, EMF induced will also be 0. So at this position, when angle is 0, angle of